Right. So I'll continue with my presentation L2. Hopefully I'll be done within an hour. Then we'll move on to the tutorial 1. So there are some slides I will discuss overall measurement details, then 2 videos, 5 minutes each. So that will conclude tutorial 1. All right, so we talked about measuring the low frequency magnetoelectric voltage coefficient. So when I say low frequency, you can start with 1 hertz and go all the way up to 1 kilohertz or more. So depending on the dimension of the composite, if it's a bilayer or a multilayer, doesn't matter. You can excite acoustic waves. So at frequencies corresponding to the frequency of the acoustic waves, you will have a quantum jump in the coupling, because the mechanical vibration is maximum under those conditions. So if the mechanical deformation is maximum, then you would get a maximum in the voltage response. So what's shown here is a bilayer under 2 conditions. One is the composite is rigidly clamped at one end, and the other option is having both ends free. So the difference is any free end will have maximum in amplitude. Any clamped end, it's 0 in amplitude. So the fundamental mode under clamping would be this mode here. And if you look carefully, there is 0 amplitude at the left end where it is clamped, and maximum on the front end. So that corresponds to lambda over 4 for the wave. Then the acoustic wave, what frequency it is. You can calculate the frequency of it. The speed of the acoustic waves. If you know the medium response. So you have to know several things in the medium to calculate theoretically the velocity or the speed. The speed is equal to lambda times the frequency. So in many of the PCT spec sheets, when you buy from the vendors, they will give you the frequency for the acoustic mode. So if it is a circular one, so they will give you the radial frequency, and if it is a long platelet, you would know that one too, for both length and the width and the thickness. So you can easily calculate where the resonance is going to be. The other alternative would be you can take a bilayer and measure the capacitance versus frequency. Wherever the resonances are, you will see a spike in the capacitance or the dielectric constant. So whenever we do the experiment, we first run the capacitance measurement, identify where the resonances are. Then when we do the frequency scan, we want to make sure we do the scan in the frequency at very small intervals, because these resonances, they're very sharp. The Q is very high, so you don't want to miss the resonance by scanning intervals of 10 hertz or 100 hertz. Okay. So I already told you why there will be a bending resonance or longitudinal resonance. If it is a bilayer, the first resonance mode is bending, because in the magnetic field or electric field, only one phase will respond by either shrinking or elongating the length. The other phase will not. There will be a bending. There is a bending resonance. But if it is a trilayer, for example, ferrite, PZT ferrite, then there is no bending, because both top and bottom will undergo either shrinking or elongation, So there is literally no bending whatsoever. The first resonance will be the longitudinal standing wave, that's the one. So that's what's shown here. If both ends free, the standing wave will have maximum amplitude. So you know the length of it, then you make that equal to lambda over 4 there. And this one half wavelength plus 1 over 4, that's 3 lambda over 4. And the third one that you see is lambda plus lambda over 4, that's 5 lambda over 4. The length is the same, the wavelength keeps, you have more waves, that means the wavelength keeps decreasing. So the frequency of the excitation will increase. So when you do the frequency scan, you will see the fundamental mode, then higher harmonics, second, third and fourth. So you can calculate all these mode frequencies. These are the equations for different numbers, F1, F2, F3. You can keep doing the calculation for the modes, and that's how it's done. Now let's see. You can also do bending resonance by loading the tip with a mass. So if you load the tip with a mass, the frequency of the oscillation will go down. It's like a simple spring and a mass. You can imagine what will happen if you keep increasing the mass. So with the mass at the tip, there is overall decrease in the bending resonance. This is used in the case of magnetic field sensors. For example, if you have a bilayer, the fundamental mode for the bending resonance, let's say it's at 100 hertz, then if I can put a 10 gram mass at the tip, the mode frequency will go down to 10 hertz. So when you superimpose the signal that you want to measure, then it will give you a lot more accuracy if you can work the sensor at lower and lower resonance frequencies. I will show you some examples. Okay. Okay, these are examples for magnetoelectric coupling at bending and radial modes. This one is it is a bilayer or a trilayer of a ferromagnetic alloy, permanent and PZT. This one, it shows resonance at 30 kilohertz. This is, I believe, it's a trilayer. There is no bending mode, and the first resonance occurs at 30 hertz. If I keep decreasing the length of the bilayer, the resonance frequency will keep increasing. Okay. As you see here, the numbers are in volts per centimeter Ørsted. Previously, when I showed the low frequency response, at low frequency, the voltage coefficient is maybe around 300 or 400 millivolts per centimeter Ørsted. This is practically 10 times that or 20 times. Okay. So there is a significant enhancement in the voltage coefficient under resonance conditions. This one is clamped at, okay, I'm sorry, this is a bilayer of permanent and PCT. It's not a trilayer. The resonance that you see there is from bending, and here there is another bilayer of a different length. It is clamped at one end. So the bending frequency is much lower. As you see here, I just want to quickly show you. When it is clamped, the length corresponds to lambda over 4. So the frequency of the resonance will be much smaller compared to the other case. So the frequency has decreased from 30 to practically around 4.5 for this case. So this is the bending resonance under a tip mass. This sample contained PCT, a layer of nickel and another layer of mid glass. So the ferromagnetic layer has two different materials. One is nickel, the other is mid glass, with three layers of mid glass. Each layer of mid glass is 25 micron in thickness. So it's 75 micron mid glass, and it's attached to PCT. These attachments were with a quick dry epoxy or some kind of bonding medium. Then you see the resonance under no tip mass. It's occurring at 110 or 120 hertz. So with 5 grams of tip mass, it shifts to 40 hertz. With 10 grams, it goes down to 25. With 20 grams, around 20. With 50 grams, close to 10. So you have the mechanism here. You have the liberty to tune the resonance to the frequency that you really want. You can manipulate the resonance, and based on what kind of magnetic field you are going to measure, you can tune the resonance. Then how do you measure the unknown AC magnetic field? It's rather easy. So you are going to use two different AC fields. One at resonance frequency, the second one that you want to measure. So when you do that, the magnetic field that you want to measure will appear as a sideband at resonance frequency plus frequency. Then there will be two peaks, one above the resonance, one below the resonance, F naught plus F naught minus F. Okay? And at low frequency, if you don't do any resonance, the voltage coefficient is close to 300 or 400. And here you are looking at 250, 300 volts per centimeter Ørsted, not millivolts, it's 1000 times more. So the field that you want to measure will appear as sideband around the resonance at that particular frequency. So all you do is measure the height of the sidebands that you can relate to the field that you want to measure. It's rather easy. You have to have a calibration curve relating known field to the voltage, then unknown field you can measure easily. Okay. So it gives you additional freedom when you design a sensor just by loading the sensor element with a tip mass. So when we do the MEMS sensor, the tip mass is an additional small mass attached to the device. So this is also resonance, but a different geometry. It is a disk. So in the case of a disk, the resonance, lateral resonance is like a breathing mode, will expand and contract. Bending will be, the whole disk will bend this way. Okay. So that's what happens. And here are the data for a disk of cobalt ferrite and PCT on the left. The center one is nickel ferrite PCT. Then on the right is lithium ferrite PCT. I am sure these are different dimensions. The disk radius, this one, the cobalt ferrite PCT is probably the largest disk, followed by the nickel ferrite, and the smallest disk is lithium ferrite PCT. But the values on the left are for cobalt ferrite, on the right is nickel ferrite and lithium ferrite, but all of them show at resonance several thousand millivolts per centimeter Ørsted. So compared to low frequency at resonance, you have very, very significant enhancement, and these are very useful when you put together different devices. So so if you have a signal generator, you apply sine waves for magnetic field, AC field, or or AC electric field, then you are going to increase or scan the frequency automatically in the system. Instead, what we did was, this is the bilayer or a multi-layer. You wind a solenoid around it like a piece of copper wire, then you pass a rectangular pulse through it. From Fourier analysis, you know that a rectangular pulse contains a whole frequency spectrum of cosine and sine waves. So you excite it with a rectangular pulse, and then you measure the voltage across PCT and pass that through a spectrum analyzer. That will show you the voltage versus frequency for all the sine and cosine waves. So that's what we did. So it's a single shot, just to pass a rectangular pulse, then measure the output, feed it through a spectrum analyzer, and then that will split everything into different frequency components. And the first peak that you see is bending resonance. Then there are radial resonances, longitudinal resonance, and then higher harmonics. That's what is seen here. Okay. So this frequency scale is in megahertz, because look at the dimension. It's 4 millimeter wide, 6 millimeter long, 1 millimeter thick. So the longitudinal resonance will happen along the 6 millimeter length. That's why it's 200 kilohertz here, 400, and all the way up to 700 kilohertz. The frequency is higher. And we didn't look at the thickness mode. It will be in tens or hundreds of megahertz. Okay, this is some theory, I'll just ignore it. Okay, so these are bending and radial modes in a disk of nickel ferrite and PZT, and see the frequency maximum, the maximum at the lowest one is the bending mode, and that value is quite high, followed by the second peak is the second harmonic of the bending mode, and the one peak at 100 kilohertz, that is the longitudinal acoustic mode. And this one here is okay, that's a bending mode F1, and this is longitudinal acoustic resonance. So since it's a disk, we call it radial mode. Okay, so we modeled what would happen in case of a nano bilayer on a substrate. In this case, it's strontium titanate substrate. The bilayer has PZT and nickel ferrite, and two different cases. One, there is no substrate, that is the peak on the very left, and then with a substrate of strontium titanate, there is clamping. The peak really shrinks a lot. As you see here, this is without it, and this is with the substrate. And these are under different conditions where V is the volume fraction for the PCT in this nano bilayer. So as the PCT volume fraction increases, you see the peak around when it is 50-50, in this case 60% PCT, 40% nickel ferrite. Then on both sides, either higher or lower volume fraction for the PCT, it decreases. Once again, these are assumed values of bulk parameters, and for a nano bilayer, truly speaking, there is no way that you are going to get this kind of values in volts per centimeter Ørsted, it will be much lower because any nano material will have parameters much lower than bulk ones. So the parameters here are the magnetostriction and the piezo-magnetic coefficient and the piezoelectric coefficient. All of them will be smaller for nano stuff. And it's a nanopillar of PZT in nickel ferrite matrix. Once again, the substrate is strontium titanate, and these calculations are for different conditions, with substrate or without substrate, and what is the volume fraction for the PCT or nickel ferrite. So I'll just pass on to the next slide. This is a coaxial nanowire on a substrate. Once again, the substrate is strontium titanate, and the coaxial nanowire is made of nickel ferrite shell. The core is PCT. You build on strontium titanate, and these are the electromechanical resonance or the longitudinal resonance along the length of the nanowire for different conditions. The conditions are that the ratio of the radius of the nanowire to the radius of the central substrate. So depending on that, as the substrate becomes bigger and bigger in radius, the overall clamping effect increases, and there is a decrease in the voltage response at resonance. Okay, so far we considered only linear magnetoelectric effect. Now, I told you that if you apply an AC magnetic field without any bias field, there will be very little magnetoelectric response. That was provided that the amplitude of the AC field is much smaller than any bias field you may apply. Instead, I can crank up the amplitude of the AC field to a very high value without any bias field. That's what this figure shows. There is zero bias magnetic field, and the AC field amplitude is pretty high. So what would happen under this condition? There is what I call frequency doubling. Just look at it here. Whether it is a positive field or negative field, the magnetostriction does not change sign. It's either positive or negative. So the piezomagnetic coefficient also will not change sign. Okay? So that would mean in the positive half of the AC field, you will get this spike here. In the negative half, you get a similar spike, maybe of lesser amplitude, because the way this is shown, it is not symmetric with respect to zero field. It is shifted slightly to the right. That means the positive amplitude is somewhat higher than negative amplitude. That's what you see in the response. But the frequency is doubled. See that? Because in one cycle here, there are two peaks. So it's doubling of the frequency. That's nonlinear effect. And you can put together a composite based on this frequency doubling circuit. Okay. All right, so far we considered only the direct magnetoelectric effect. That's the influence of the magnetic field on the piezoelectric order parameters. It can be an induced polarization or a voltage or a change in the dielectric constant. Later in this course, I am going to talk about other types of measurements where you can look at the dielectric constant, apply a magnetic field. There will be a change in the dielectric constant. That's evidence for magnetoelectric coupling. And also, you can do P versus E for the ferroelectric phase, apply a magnetic field, there will be a change in the remnant polarization. That's another evidence for magnetoelectric coupling. And so there are other measurements which I will talk about later on. But we are now turning to converse magnetoelectric effect, where the studies are aimed at what happens to the ferromagnetic phase if I apply an electric field to the composite. So there are two types of major measurements for this. One is ferromagnetic resonance under an electric field. The other is you can measure magnetization versus static field, M versus H, the traditional hysteresis, then apply an electric field, look for change in the magnetization because of that. Okay. Now this one is what I am talking about, ferromagnetic resonance under electric field, and this is M versus H under an electric field. You can do either one. The third option would be to use a scanning probe microscope, do magnetic force microscopy, image the domains, get data on the phase and the amplitude of MFM, then apply a voltage, then look for any change. That you can come up with a number that would quantify the strength of the magnetoelectric coupling. But for now, we will focus on these two types of measurements. What's shown here is a traditional ferromagnetic resonance under no electric field. So what is ferromagnetic resonance? Now if there is a ferromagnet, you apply a static magnetic field, the magnetization will precess around the applied magnetic field. It's called Lammer's precession. It has a finite frequency. Okay. Now on top of that, if I apply an AC magnetic field at appropriate frequency, what's going to happen is, this is DC field, the magnetization precesses. I apply an RF AC magnetic field in the perpendicular direction, so it will produce a torque. It will keep increasing the angle of precession about the DC field. Now if it is electron spin resonance, you can flip the motion from up to down all the way, because electrons they are completely isolated. There is no collective excitation. But in case of a ferromagnet, you have all these spins parallel to each other. They are coupled with exchange interaction. So you cannot flip it. It requires huge energy to flip the whole magnetization. But what will happen is the angle of precession will open up. So there is transfer of energy from the microwave field to the spin system. That's called resonance. That will appear as so that appears as a peak in the power absorbed by the sample. There is transfer of power from the microwave field to the system. That will show up as a peak in the power absorbed, and this can be done by several means. You can but you have to satisfy the resonance condition. I told you this, the magnetization precesses around the field at a particular frequency. So you have to match the frequency of the microwave to that precession frequency. When you do that, it happens. So there are two options. One is you can fix the static magnetic field, scan the frequency, you will see the resonance. Okay. The second option is you can fix the frequency of the microwave, then scan the magnetic field, then you can see the resonance as an absorption here. In most of the cases, what we do is we don't measure the power absorbed, we measure the derivative of the power absorbed. So that would show up as this one here. So what you see here is look at this, the power absorbed increases reaches a peak, then it drops down. If I take derivative of this absorption curve, it will keep increasing. At the peak, the slope is 0, right? So it will cross the origin. Then, so it will show up as a down peak, and wherever it crosses the 0, that is the resonance condition. Then it goes up all the way, and then it comes back down. So these are theoretical simulation for the 3 different systems of bilayers. One is yttrium iron garnet with PZT, the other is nickel ferrite and PZT, the third one is lithium ferrite and PZT. And the profiles are shown for 2 conditions. One is no electric field applied to PZT, and the second one is a field of 300 kilovolts per centimeter. That's a really high, very high field. But for theory, you can assume whatever field you want. There is no harm. Okay. So as you see here, under no field, you see the resonance. When the electric field is applied, there is a shift in the resonance to the right. So the resonance occurs at a lower static field. So we can calculate what is the shift in the resonance field, that's delta He. And if you do the theory, it is proportional to the product of the magnetostriction multiplied by the stress parameter T33, and it is inversely proportional to the magnetization for the ferromagnet. So the ratio of the shift in the resonance field to the applied electric field, that is converse magnetoelectric coefficient. Okay. So for these 3 systems, for a field of 300 kilovolts per centimeter, the shift for lithium ferrite is 75 Oersted. So the coefficient for the converse magnetoelectric effect is shift divided by E. So that's 75 Oersted divided by 300 kilovolts per centimeter. So you end up with 0.25 Oersted centimeter per kilovolt for the first one. For the second one, it's nickel ferrite PZT, the shift is 300 Oersted. So the coefficient A would be 1 Oersted centimeter divided by kilovolt. Egg PCT is even much smaller. And this is when you do the field scan. If I do the frequency scan, which I am going to show next, 1 Oersted corresponds to about 3 megahertz. So I don't want to give you too much information now and confuse you, but take for granted that we can do this experiment under frequency scan or field scan. This is the theory for if you scan the field, these are the profiles, and this is what you expect. And how do you do the experiment? This is a traditional Bruker ESR spectrometer. It can be used for electron spin resonance or ferromagnetic resonance. And there is a microwave source which is enclosed in the box sitting on the top. So there is a microwave circuit. There are some waveguides. At the end of the waveguide, there is a cavity. Cavity, you excite standing waves, you store electromagnetic energy, right? Then you put a sample in the middle of this cavity, and then frequency is constant, you scan the field. So when there is resonance, there is transfer of power from the microwave radiation to the sample. You see the spike. So what actually happens is, under resonance, the cavity Q will decrease, so it will reflect more power. That's what shows up as the spike in the power. Under no resonance, the cavity Q may be 10,000. So when it starts to absorb power, it will go down to maybe 1,000. and then the cavity will reflect more power, and that's what is seen as the spike. Now, these are some of the experiments that we did with a bilayer of yttrium and garnet bonded to PM&PT platelet, and you see several spikes here. These are the main one shows up with that is the main resonance. These are what we call magnetostatic modes. Just ignore it. For no electric field, then you increase the electric field, and from 1 kilovolt per centimeter to 6, you see the peak shifting to the right. And what is plotted here is the electric field versus the field shift in resonance, which is linear. You take the slope of this, that is the converse magnetoelectric voltage coefficient. Okay. So this is the other method where you can do converse magnetoelectric effect by frequency scanning of the FMR. So this one here is what we call a strip line microwave structure. It has a single metallic patterned. There is a ground plane made of alumina. Then there is a single strip of metal. Then when you pass microwave through this strip, there is current. And we know that if there is a current, there is always a magnetic field, correct? So it will produce a microwave magnetic field. So the current is flowing this way. The field, from the right hand rule, it will be a circular path around the current. So there will be a component of the microwave field perpendicular to that. So then the basic, the bias magnetic field is applied perpendicular to the bilayer of egg and PCT. The yttrium and garnet is on a substrate of gadolinium gallium garnet, that's GGG. So it's placed on top. You excite with microwave power, then a constant bias magnetic field. You scan the frequency, and the resonance shows up as a dip. Why there is a dip? You measure the power reflected. So there is a vector network analyzer that provides the necessary power, and the power reflected is measured. Now the power reflected will decrease under ferromagnetic resonance because the sample will absorb power, so the reflected power has to decrease, and the dip is, this is where the resonance frequency is. So from the equation for ferromagnetic resonance, you can calculate the shift, and then this is no electric field. If you apply an electric field, it shows a downshift in the frequency. So from this difference and the magnitude of the electric field applied, you can calculate what the converse magnetoelectric coefficient is. So that's how we do the converse effect. This one shows what would happen, what we measured when we used yttrium and garnet PCT or egg PM and PT, and it's just a simple calculation based on whatever shift we measure here. Okay. Then I just mentioned that you can also do converse magnetoelectric effect using a scanning probe microscope. How many of you are familiar with scanning probe microscopes? Okay. All right. So it's the scanning probe microscope for thin films. You can look at the surface profile, magnetic domains, and ferroelectric domains with different tapes at nanometer resolution. These are microscopes similar in principle to an electron microscope, but they have different excitation, driving force, and you can come up with a neat figure or an image of the surface of the film. And also there are several different images depending on what you are interested in. So one of them is using this to look at the ferroelectric domain pattern. So what this one shows is there is a composite of some material, some composite material, and then you look at the piezo force microscopy in terms of amplitude and phase, which will show the domains. Then you apply an electric field that will lead to, depending on the voltage that you apply, the ferroelectric domain might expand in size or contract in size. If that's the case, then what I can do is, you have a composite of a ferroelectric and a ferromagnet, right? So I want to look at the converse magnetoelectric effect. So you look for the magnetic force microscopy and essentially look at magnetic domains. Then you apply an electric field to the tape, which will affect the ferroelectric phase. That will lead to interaction with the magnetic phase, and you would see a numerical change in the amplitude and the phase of the MFM signal. That would be a measure of the magnetoelectric coupling. Or otherwise, you can look at the ferroelectric domains using PFM. Then you apply a magnetic field, and you will see a change in the PFM amplitude and phase. That is shown in this picture. These are PFM patterns, and there is a typo here. A should be minus 600 Oersted. B is, there is no magnetic field. C is under plus 300, and D is under plus 600. As you go from minus 600 to 0, plus 300 and 600, you see a significant change in the PFM signal, and you can measure the phase and the amplitude and come up with a magnitude for the coupling. This particular sample has lead titanate and nickel ferrite of that particular composition. Nickel ferrite with that composition is a ferromagnet, and lead titanate is a ferroelectric. So to summarize, I talked about magnetoelectric composites and the low frequency magnetoelectric effects and then resonance effects. We modeled different types of composites, and I didn't want to dwell on each and every model results, because first of all they are not accurate in terms of magnitude, because we are using parameters meant for bulk materials, and second is we don't have experiments to compare with theory. So, but I just wanted to give you a feel for what would happen in composites with different types and nanomaterials and versus bulk samples. And also we talked about the direct magnetoelectric effect and resonances corresponding to both acoustic resonance at bending as well as longitudinal or radial modes. Then converse magnetoelectric effect, how you look at it with FMR, and then using scanning probe microscopy to do these measurements. Okay, right. That takes care of lecture number 2. Now I will go to the tutorial T1. Any questions?